This is the Olivetti Prodest PC1, and as far as I know, it's the only IBM-compatible PC from the 1980s with a true RGB DAC capable of 512 colors. In that sense, it stands surprisingly close to machines like the Amiga, which outputs 4096 colors. The PC1 gives us 3 bits per RGB channel, the Amiga gives us 4. But the important part is this: the PC1 can change colors every scanline, and with the right tricks, maybe even multiple times within a scanline, just like the classic copy tricks on the Amiga. What the PC1 doesn't have is hardware sprites. What it does have is one hardware mouse pointer, and that turns out to be enough to do some very unexpected things. And in this video, I'll take you along on my journey to explore what this little 1980s machine is actually capable of. You'll see the breakthroughs, the failures, the dead ends, and the moments where everything suddenly clicks. From Sprite multiplexing to palette RAM effects, raster bars, bizarre hardware quirks, and scrolling experiments that almost worked, and sometimes did work. So let's dive in. Chapter 1. Using the mouse sprite. The PC1 has a single hardware sprite, normally used as a mouse pointer. In this chapter, we will hijack it as a game sprite and try to show multiple bouncing balls from just that one sprite. First, one bouncing ball. This is the starting point. One ball, one sprite, nothing fancy. It shows how to set up the sprite using the mouse driver, and then define a round shape and bounce it around the screen. B-balls 1, 3 balls via the mouse driver. Now we are trying 3 balls with one sprite. The idea is to quickly move the sprite between 3 positions so fast that your eyes sees all 3. But it doesn't work very well. There's visible flicker because we are just guessing when to move the sprite. There is no synchronizations with the screen. The code is also messy. The same bouncing routine is copy-pasted 3 times. B-balls 2, 3 balls via direct hardware. Same idea as B-balls 1, but instead of going through the mouse driver, we are talking directly to the V6355 video chip. This is faster because there's no driver overhead. But the fundamental problem is still the same. We're still not synchronized to the screen, so it still flickers. Faster doesn't fix the real issue. B-balls 3. 1 ball per frame. Here we add proper screen synchronization. We wait for the monitor to finish drawing before doing anything. Good idea, but bad execution. Instead of showing all 3 balls in one frame, it shows only 1 ball per frame and cycles through them. Ball 1, then ball 2, then ball 3. Then back to ball 1. Each ball only appears every 3rd frame, which is about 17 Hz. Your eye can see that. It actually flickers worse than B-balls 1 and 2. So this is a dead end. Okay, chapter 2. Sprite multiplexing. This is where we figure out the right way to do it. This is the solution. The screen draws top to bottom, line to line. It's called scanlines. Actually, we need to explain scanlines. Scanline is if you look at the screen like there was a laser pointing at it and drawing the lines. You will see the laser moving from left to right, and then go all the way back again to the left and continue and draw the next line. That is how the graphics card operate when they are drawing lines on a screen, and that is called a scanline or scan lines. So we use that to put the sprite at the top ball's position, wait for the screen beam, this laser, to pass it, then quickly move the sprite down to the second ball's position. The screen draws both, no flicker. 2 balls from one sprite, but visible every single frame. Next, B-Balls 5. Here we are adding colors. It's the same raster sync trick as B-Balls 4, but now with visual polish. Each ball gets a random rainbow color every time it bounces. The top ball is drawn in XOR mode, so it's transparent. You can see through it. Talking in terms of scanlines, the colors and mode changes mid-frame between the 2 balls' position. B-Balls 6. Here we are adding sprite animation. This is the final sprite version. On top of everything B-Balls 5 does, the sprite shape now animates. It's a spinning line that rotates through 8 frames. The sprite data is uploaded to the video chip mid-frame, so each ball can even have a different animation frame. This is the ultimate showcase. 2 animated, colorful sprites from a single hardware sprite, perfectly flicker-free. Chapter 3. Port Color Raster Bars. These demos create colorful horizontal stripes effects without drawing any pixels. The screen memory is filled with zeros and never changes. Instead, we change the color index the whole scanline uses, perfectly timed to the horizontal sync. But before we continue, we need to explain horizontal sync, vertical sync, HBLANK and vertical blank. So, horizontal sync, that is the term for when the drawing of one scanline is finished. Then we receive or we can ask for a horizontal sync signal. The same when the whole screen is drawn, that is called a vertical sync, when we are finished with the screen and the beam is leaving it. That's the vertical sync. And then we also have HBLANK and VBLANK. So the HBLANK, it's the time between we are finished drawing one scanline and the beam is going back to start drawing the next scanline. That time frame is called HBLANK or horizontal blank. And we have the same for the vertical sync. It's called the vertical blank, and that is the time from when the beam leaves the bottom line and goes all the way back on top of the screen again to continue drawing scanline 0. And in many games, in many computers, the game logic usually runs here, in that blank time. Sprite tables, they are updated here. Large VRAM transfers occur here. Essentially, VSync is the big blank area between the frames that we can use to do stuff. During HBLANK and VBLANK is where you can safely change screen registers without visible glitches or flickering. Okay, so first demo, Raster Bars 1. This is the simplest test. It changes the colors once per scanline using the port color registered. This is the simplest test we can do. We change the color once per scanline using the port color register. In the PC1 and ordinary CGA, it's register 3D9, and it's how we change color in assembly. The important discovery I made creating this demo was that the colors only appeared in the border area, not the full screen as we can see here. It turns out we need to write register 40 to port 3DD to unlock full width mode. Without it, port color only affects the border. Writing 80 to port 3DD locks it back to border only. Okay, the raster bar demo 2. This is a single gradient bar that scrolls down the screen. But something looks off. The colors are only one scanline thick and no black between the bars, giving thin stripes instead of a smooth bar. This demo has some interactive controls to toggle the full screen vs border only. So let's press U, and that basically toggles full screen or border only. I can press E to turn off H-Sync, and then you can see all the stripe, everything is done at the top. And we can turn on and off V-Sync, and does not do much, but if I turn off H-Sync and then off V-Sync, we get this. So I just created this to get a better understanding of how V-Sync, toggling V-Sync and H-Sync would work. Next out is raster bars 3, and this fixes the thin stripe problem from raster bars 2. Instead of changing color every line, it uses division. So color equals the scanline number divided by 12. This means 12 consecutive scanlines all get the same color, creating a thick, solid band. The color still gets written every scanline. You have to stay in sync, but the value only changes every 12th line. Raster bars 4. Now we are combining the thick bands with a gradient effect. Each bar has a bright center fading to dark edges, like a glowing stripe. Multiple bars are evenly spaced using modulo math. But there's a visible problem: tearing. The gradient calculation starts during horizontal blank, but the 15 instructions of the maths are taking too long and continues into the visible part of the scanline, causing a delayed color change and visible tearing. Okay, raster bars 5. This fixes raster bars 4 tearing problem. Instead of calculating the colors during the scanline loop, all 200 colors are pre-computed into a lookup table before the frame starts. The render loop becomes just 3 operations: wait for sync, load a byte from the table, write it to port color. No math, no delay, no tearing. The classic Demoscene lessons is trade memory for speed. And raster bars 6. A different kind of animation. The bars stays in the same position on screen. The pattern table doesn't change. Instead, the actual RGB colors stored in the pattern entries are rotated every frame during vertical blank. You know that blank area before the while the scanline is leaving the screen at the bottom and coming back at the top. So that's the area we're working within. What was blue becomes green, green becomes yellow, and so on. The color flows through the bars like liquid. It's the classic C64 palette cycling trick. Animate without changing any screen data, just shuffle the palettes. Raster bars 7. This is my most advanced raster bar demo. 2 bars, each moving independently with a sine wave motion. Smooth bouncing up and down at different speeds. When the bars cross each other, they swap which one draws in front, creating a 3D dancing illusion. This combines several techniques like pre-computed tables, gradient math, and sine wave physics, and depth sorting. How cool is that? Chapter 4, Bitmap stuff. This folder we are looking through the demos on now is a journey. It starts with how do I even show a bitmap on screen, and it ends with can I scroll a tall image using only 160 bytes per frame instead of the whole 16 kilobytes? The answer turns out to be almost, but the hardware has a nasty surprise hiding in its memory layout. All these demos load a 4-bit BMP file from disk and displays it in the PC1's hidden 160 x 200 graphics mode with 16 colors. And all that in only 16 kilobytes of video RAM. So let's start the first demo. We already know from folder 3 or chapter 3 that port color can change the background color on every scanline. That's how raster bars work. So naturally, what if we load an image and draw raster bars on top? Well, turns out it doesn't work. Or rather, it only half works. Port colors only shows through a scanline where all pixels are colored 0 or blank lines. On any line with actual image pixels, the graphics chips block the override. The bars only appear in empty parts of the screen and in the border area. So this demo is really about discovering a limitation. We can see the bars dancing around with a knife's Sine wave wobble, swapping depth and then cross each other, but they vanish where the image has content. One small optimization worth mentioning. This demo uses the 8-bit port alias 0xD9 instead of the full CGA address 0x3D9. That means that the out instructions doesn't need to set up DX, saving a few clock cycles per scanline, enough to make the difference between stable and flickery. Demo 2. Since port color cannot draw over image pixels, we try a completely different approach. Instead of changing the background color per scanline, we are actually writing pixel into video RAM. Solid horizontal stripes using palette entries 14 and 15. The clever part is that the color animation doesn't touch VRAM at all. We just write new colors into the palette entries 14 and 15. By doing this, every vertical blank, every pixel that uses those two color palettes entries instantly change color. This is just a 4 byte of I/O per frame for smooth color cycling. The problem here is erasing the bars when they move. We need to put the original image pixels back, and to do that, we back up the VRAM scanlines before drawing. But reading from VRAM is slow on this hardware. That's what Demo 3 tries to fix. So, Demo 3. Same idea as Demo 2, but instead of backing up VRAM scanlines, we keep a copy of the whole image in RAM buffer. When we need to erase the bars, we restore from RAM, which is much faster than reading from video memory. It's a good idea, but this implementation has a bug. The palette cycling doesn't work properly in these versions. The bars move, but the colors don't animate. And that's our segue over to Demo 4. This is demo 3 done right, loading the image into RAM first, then copying to VRAM. Bars are drawn as VRAM stripes with palette cycling for the color animation. Smooth gradient, breathing effect, everything works. Demo 5. Time for some education. CGA VRAM is non-linear. Instead of storing scan lines in normal order, row 0, row 1, row 2, etc., it stores all the even scan lines in one block and all the odd scan lines in another block. This matches how the CGA hardware fetches pixels during display. EGA and VGA do not use this layout. They both use linear addressing inside each plane, so scan lines are stored normally in memory. Now you might think this means that CGA draws the screen interlaced, but it doesn't. Only the VRAM layout is interlaced. The CRT still draws the scan line in normal orders. We need to understand this layout so we can correctly optimize video copying. So now we are moving on to scrolling, but I promise you we will come back to some more raster bars and techniques in chapter 5. This demo loads a BMP image and pans it around the screen in a smooth Lee Su pattern. The X and Y axis moves on independent sine waves, so the image makes a beautiful figure eight motion. The key optimization in this demo is the RAM buffer layout. Instead of storing the image linear in RAM, we store it non-linear, mirroring how CGA RAM works. Even rows in one block, odd rows in another. This means we can copy entire banks in one big rep moves SV, instead of calculating which bank each row belongs to. Every frame copies the full 16 kilobytes to VFrame. That's a lot of data. You can see some tearing because the copy extends past the vertical blank period. Okay, demo 5 B and C. These two are a pair. Same scroller, same motion, but demo 5B uses a linear RAM buffer and demo 5C uses an interleaved one. They exist specifically to compare the two approaches. The raster bars from earlier demos are disabled in both, so we're only measuring the scroll performance, nothing else. Linear RAM is easy to understand. Each row sits directly after the previous one. But when copying into CGA VRAM, we have to check for every row whether it belongs in the even line bank or the odd line bank. Interlaced RAM matches CGA's layout, so you can copy each block in one go, without doing any per row bank logic. Just blast the even block and then blast the odd block. Okay, we have still a lot of things to learn, so demo 6. What if we don't update the whole screen? Demo 6 only moves part of the image. By default, we are moving 50 rows out of 200. That's 75% less data to copy each frame. The big invention here is delta clearing. Earlier demos would clear the old position, then draw the new one, which creates a visible flash. Demo 6 is smarter. It only clears the rows that are newly exposed. If the image moves on, it clears the top rows, the image left behind. If it moves up, it clears the bottom. No gap, no flash. I've also added our FPS counter that updates once per second. With 50 rows of motion, it hits about 50 FPS with VSync enabled. And disabling it by pressing V, we get about 72 FPS. The math says you can push it to about 74 rows before you drop below 50 FPS. Moving on to demo 7. Now it's starting to get really interesting. We are looking into hardware scrolling on the Olivetti PC1. What if we could scroll without copying any pixels? CGA-compatible video registers have register R12 and R13, the start address. They tell the display controller start reading VRAM from this address instead of the top. Changing the address and the whole screen shifts instantly. 0 CPU cost, just 2 register writes. Demo 7 proves this works. On the PC1 graphics chips, you can scroll up and down with the arrow keys and the image moves with absolutely no pixel copying. It feels instant. How great is that? But there's a catch. If you scroll far enough past one screenful and the image shifts about 96 pixels to the right. That's the 192 byte bank gap. Each CGA bank is 8,192 bytes, but only 8,000 are used for display. Then the CRTC reads past byte 8,000. It hits that 192 byte gap of garbage, and everything after that is shifted. This is a fundamental limitation of CGA interlaced mode. The gap is always there. You cannot make it go away, and R1213 reads right through it. For small offset, maybe 5 row, it's 5. For actually scrolling, it's broken. In demo 7b, we are trying software scrolling. So R12/R13 register writing cannot scroll a tall image on CGA. So back to software. Demo 7 takes the brute force approach. Load a tall image, up in this case up to 800 rows, well beyond what fits in VRAM, into a DOS allocated RAM buffer. Then copy whichever 200 row viewport you want to see into VRAM. Move the viewport, copy again. It's not clever, but it works. 2 ret move sui operations per frame, one for the even bank and one for the odd bank. No per row calculations, no clipping logic, simple and reliable. You can scroll manually with the arrow keys or press space for auto scroll where it bounces up and down. They cost 16 kilobytes per scroll step. Every time you move, you are copying the entire screen. And that's our segue into Demo 8. Demo 8A. This is the demo I was most excited about and most frustrated by. The idea is beautiful. Treat VRAM as a circular buffer. When you scroll down by 2 rows, you don't need to redraw the whole screen. 198 of the 200 rows are the same. They just moved up. Only 2 new rows appears at the bottom. So just overwrite the 2 rows that scrolled off the screen with the 2 new rows. Then tell register 12 and 13 to start reading 2 rows later. The CRTC wraps around at the back boundary and reads everything in the right order. So instead of copying 16 kilobytes per frame, you copy 160 bytes. That's a potential 100 times speed up. And it works for exactly one scroll step. Then the gap hits. Remember those 192 bytes of unused space at the end of each bank? Well, the circular buffer needs the CRTC to wrap cleanly from the bottom of the bank to the top, but it doesn't. It reads through the gap first, displaying garbage. This demo exists as a proof that the concept works in principle, even though CGA interlacing kills it in practice. And that's without VSync. Demo 8C, True Circular Buffer. If the gap is 192 bytes and we need more headroom, what if we make the visible area smaller, but do it properly? Demo 8C uses register X65 on the V6355D to set genuine 192 line mode. That means each bank uses 96 rows times 80 bytes equals 7,680 bytes instead of 8,000. The gap grows from 192 to 512 bytes. And there's the key insight. That's enough for the CRTC to wrap around the full 8K bank boundary without ever reading garbage data. So instead of periodic reloads, we get a true circular buffer. Every single scroll writes exactly 160 bytes, the two new rows that appear at the edge of the screen. The CRTC's MA counter wraps naturally at 8,192, which is standard CGA 6845 behavior. On the rare occasion where a row straddles the bank boundary, about 1 in every 102 scrolls, the copy is split into two parts, but it's still just 160 bytes. So we get no reloads, no stutter, no compromise. Every frame has identical cost, 160 bytes, roughly 96 times faster than the 15 kilobyte software copy in Demo 7B. You lose 8 rows of screen height, but you gain perfectly smooth scrolling, confirmed on real hardware. So, the last demo in Chapter 4, Demo 9. After all that frustration with the gap, this demo asks, what can we do with the R12 and 13 if we stay within the safe zone? The answer is quite a lot, as long as the offset stays small. Demo 9 loads an image and offers a menu of effects, all done purely through start address manipulation. So the first one I'm going to show you is the screen shake. So I can press S and we can see we get a screen shake. Look like an earthquake or an explosion. We can press H for a horizontal wave. It's a sinus oidal wobble, and the whole screen sways side to side. Pressing T, we get an image slide in from the left, like a transition. And B, we can bounce it, and a horizontal bouncing animation. And M, it's like a ping-pong scroller, or like a news ticker coming in from the side. And every one of these are essential free. It's one register write per frame, so no pixel copying. The CPU barely does any work. That's the power of hardware registers when you work within their limits. So, to wrap it up, if there is one takeaway from folder 4 or chapter 4, it's that hardware limitations aren't just obstacles. They are what force you to be creative. The 384 byte gap in the CGA memory is an obscure quirk that most programmers never even noticed. But when you try to build a circular buffer scroller, it becomes the most important thing in the world. And the solution so far is to reduce the display height, accept period stutters, or just give up and copy 16 kilobytes. Chapter 5. I promised you to come back to more raster demos. While in folder 3, we showed how to create raster bars using port color. You know, the CGA background color register. That technique is fast and simple, but it has one huge limitation. Port color only changes the background color. If a scanline contains any real image pixels, like non-zero color values, the graphics chip will draw those instead and ignore the port color override entirely. That's why raster bars in chapter 3 only appears in border area, on lines where the image contains zeros, or in a special blank frame buffer. It's a powerful trick, but only as long as the screen is empty. So here comes chapter 5. It's a completely different technique. Instead of changing the background color, we change the palette RAM itself, the actual RGB values stored inside the hardware's 16-color DAC. Every pixel on screen uses a palette index from 0 to 15, and that index looks up its real color palette in RAM. So when we modify those palette entries, every pixel that uses that index changes colors instantly, even over real images. No need for blank scanlines, no need for color 0 pixels. This method works on full graphics, full images, sprites, pictures, anything. So, where port color is background only, palette RAM affects the entire picture. And the PC1's DAC is fast. It lets you update one palette entry every scanline. So there is enough bandwidth for 200 color gradients, animated color flows, multi-band raster bars, Sine wave color motion, and more. And all without touching a single pixel in VRAM. So that is what chapter 5 explores. One more thing before we start. It's important to understand why the PC1 can pull off all these palette RAM tricks at all. Unlike normal CGA, which is locked to a 16 fixed RGB colors, the Olivetti Prodest PC1 has a real RGB DAC with 3 bits per channel, giving 512 possible colors on screen. This suddenly puts the PC1 much closer to machines like the Amiga with its 4096 colors or the Atari ST with its 512 colors. Because the palette entries aren't fixed, they are fully programmable. And the most important part of this chapter, the PC1 let us change these palette entries on every single scanline. How great is that? Okay, first demo, PalRAM 1. This demo shows how the PC1 can display a smooth vertical gradient with lots of colors, one for each scanline. It does this by changing the color palette on every line, synchronized with the screen refresh. It's simple It's a clean example of how palette RAM can be used for colorful effects that go beyond what you expect from old hardware like this. Building on the first demo, this one adds animation. The gradient now moves or cycles, showing that you can animate colors smoothly just by updating the palette RAM in sync with the screen. Skipping to PalRAM 5, this demo pushes the hardware to its limits, showing what happens when you try to update the palette too quickly or with too many colors per line. You will see jitter or instability. This is evidence of the timing challenges when raising the beam on vintage hardware. Chapter 6 is about a programmable interval timer. Before we dive into these demos, we need to talk about the PIT, the programmable interval timer inside every PC-compatible machine. The PIT is a small hardware timer chip that generates periodic interrupts at precise intervals. Its job was mundane: drive the system clock, control the speaker, and help with timing in DOS programs. Just because it can fire interrupts at custom frequencies, the PIT can also be bent into interesting uses. One of the most creative uses of the PIT appears in old-school demos. Using the timer to drive raster effects. Instead of synchronizing to the video hardware itself, horizontal sync or vertical sync, like we have done, we are trying to fire interrupts fast enough and accurately enough that each interrupt line up with a particular scan line. This approach was famously pushed to the extreme in several cutting-edge demos on slow 8088 class machines, where clever PIT programming was used to create the illusion of mid-scanline effects even on hardware that was never designed for it. Of course, the PIT was never meant to be a perfect raster timer. It has jitter, interrupt latency varies, and the CPU may be busy doing something else when the timer fires. So PIT-driven raster effects are always a bit unstable. They shimmer, they wobble, or drift slightly. But that's part of what makes them fun to explore. So we have 3 demos here to show you. PITRAS 1. This demo uses the PIT to create a color effect on each scan line. Instead of relying on the usual vertical or horizontal sync, it's an experiment to see if timer interrupts can be used for smooth raster effects. You'll notice some limitations. Timing isn't perfect, and the effects aren't as stable as with direct sync. Here, the program tries to update several palette entries per scanline using the PIT. The result, you'll see that the hardware just cannot keep up, and the colors get messy. It's a clear demonstration of why only one palette entry can be changed per scanline on this machine, at least with my programming. This demo lets you experiment with changing colors in the middle of the scanline, aiming for a split screen effect. You can control the PIT to adjust exactly when the color change happens, allowing you to hunt for the perfect timing. By pressing the plus and minus key and arrow up and down, this program is designed to help you explore and fine-tune these timings. Because of time jitters and hardware limits, the split isn't perfectly sharp. It wobbles. Maybe you can use the program to find the perfect timings. Chapter 7: CGA Palette Flip. Before we dive in, let's talk about the CGA palette flip trick. On classic CGA hardware, we are limited to just 4 colors on the screen at a time, chosen from a small set of fixed palettes. But there is a clever trick. The CGA actually has two palettes, palette 0 and palette 1, that you can switch between by writing a single byte to a port. If you flip between them fast enough, alternating on every scanline, you can display more colors than the hardware was ever meant to. On the PC1, the Yamaha V6355D chip makes this even more interesting. Unlike CGA, every palette entry is fully programmable to any of the 512 RGB colors. I want to give a special thanks to Simon, who made this exploration possible. Simon sent me photos of running with lots of colors on his PC1, which proved the technique worked. Without that encouragement, I might never have tried pushing the PC1's palette hardware this far. CGA Flip 2, my first attempt. This is the very first working palette flip demo. It flips the palette every scanline and tries to update palette entry 0 with a new color during each horizontal blank. The gradient works, but the borders flickers. That's because in CGA entry 0 controls both the background pixel and the border. When you change it every scanline, the border cannot settle on a single color, and the lesson learned is that don't touch entry 0 if you want a clean border. CGA Flip 4. What doesn't work? After getting the flip working, the obvious next question was, can we update all the palette entries every scanline? If so, every line could have completely different colors. This demo tries exactly that. It flips the palette during horizontal blank, then streams all 8 palette entries during the visible part of the scanline. The result, blinking. The V6355 chip doesn't like when you open and close the palette write session while it's actively drawing pixels. This was a dead end, or so I thought. CGA Flip 6, the safe approach. After the CGA Flip 4 failure, I went back to basic. What if we do no palette streaming at all, just the flip? This demo does exactly one port write per scanline, the palette flip. To get more visual variety, it uses a different trick. The VRAM itself holds different pixels values on even and odd scanlines. Combined with the palette flip, this creates a sunset gradient effect, with 7 perceived colors through perpetual blending. Perfectly stable, 0 flicker. Looks okay, but it's limited to the colors you set once at the start. CGA Flip 7. This one was meant to be my final demo on the subject. At this point, I thought we'd hit the ceiling. We could only update one palette entry per horizontal blank. And to give 3 columns their own gradients, each column only gets a new color every 6th line. CGA Flip 7 was supposed to be the showcase of what was possible within those limits. 3 coarse gradient columns with about 85 unique colors, using a clever VRAM rotation trick to share that single entry across all 3 colors. 0 flicker, and honestly, it looks pretty good. But while building this, I discovered something that changed everything. The deferred open-close technique. Instead of opening and closing the palette write session within the same horizontal blank, CGA Flip 7 opens the session on one line and leaves it open until the next. The chip is perfectly fine with that. It's only the opening and closing that causes blinking, not having an open session while the screen is being drawn. That discovery meant the door was open to stream more colors than one entry per horizontal blank, which led straight to CGA Flip 9. CGA Flip 9, 512 colors. This is the culmination of the CGA Flip part. On every even horizontal blank, CGA 9 streams all 6 visible palette entries, setting colors for both the current line and the next one in a single burst. The current scanline get their new value written while they're still starting to be drawn, and the upcoming entries gets preloaded with the next line's colors. No complicated VRAM tricks needed. Every column gets its own independent color on every single scanline. There is one constraint. Because the registers are written sequentially, the last register in the burst, entry 6, doesn't finish until after the beam enters the visible area. This means the column order is load-bearing. E6 must be placed in the rightmost column so the beam doesn't reach it before the write completes. This is a serious constraint, but there are workarounds. You can ensure palette entry E6 isn't used in the first 100 pixels or so, or you can give E6 a static color. Since the stale value equals the new value, the artifact becomes invisible. This demo has 4 modes. You can cycle through them with spacebar. The smooth gradient triplets, an RGB test pattern, all 512 colors displayed at once, and a 200-step smooth gradient. All perfectly stable, all running on real hardware from 1987. Before we end this video, we need to circle back to the images we started this video with. The PC1 BMP viewer. This is the foundational demo for displaying bitmap images on the Olivetti Prodest PC1. It starts by loading a custom palette from the image file, which it then uses to create a loading screen like the C64 has, using the same raster bar technique demonstrated in Demo 3. The purpose is to use the PC1's hidden 160x200 16-color graphics mode on the PC1. This mode is a trade-off. You get more colors, 16 from a palette of 512, but half the horizontal resolution compared to the usual 320x200 CGA mode. My program automatically converts standard 320x200 images down to 160x200, so you can use regular PC bitmaps as your source. But I also created 2 more versions of the viewer. My second viewer is called PC1 BMP2, and it uses the CGA palette flip trick. This version uses CGA 320x200 mode combined with CGA palette flipping, thanks to Simon, who first demonstrated it on the Olivetti PC1. The trick is to set CGA palette flipping one every scanline. The program flips between 2 CGA palettes and streams new color values into the palette during horizontal blank. This is the same per Scanline palette reprogramming technique explored in CGA Flip 9, but here it's used to display actual images instead of simple gradients. However, there's an important difference in how the palette is updated. In the gradient demo, the program writes to both the active and inactive palette entries in a single burst. This is fast, using fewer I/O operations per scanline, but it means that the last entries are written after the beam has already started drawing pixels. That's fine for the gradient demo because we control the screen layout. The late written entries is placed in the rightmost column where the beam hasn't arrived yet. But for an arbitrary BMP image, any color can appear at any horizontal position. If a late written color appear on the left side of the screen, you'd see a brief flash of the wrong color before the new values take effect. So, in the BMP viewer, we have a different approach. The flip is the very first thing that happens after horizontal blank, instantly revealing colors that were preloaded into the inactive entries during the previous scanline. Then, all palette writes targets only the currently inactive entries, preloading colors for 2 scanlines ahead. This means the writes never affect what's currently being displayed, so all 3 colors can appear freely at any pixel position with no artifacts. The trade-off is 2 extra I/O operations per scanline to open and close the palette write. But since we are displaying a static image and don't need the saved cycles for animation or sound, it's the right choice for maximum image quality. Each scanline gets 3 independent non-black colors chosen from the full RGB palette of 512 possible colors. Since the palette is reprogrammed every scanline, different lines can use different colors, meaning theoretically all 512 colors could appear in a single image, as long as no individual scanline needs more than 3 non-black colors. When a scanline does have more than 3 colors in the original image, the extra colors are remapped to the nearest match. The VRAM pixel data is written once during loading and never changes after that. All the color magic happens entirely through palette reprogramming. Palette entries 0 and 1 are always kept black, since entry 0 is the shared background and border color. The actual image colors live in entries 2 to 7, which alternates between active and inactive on even and odd scanlines. I've also made a third version, and that adds dithering. So this version builds on the previous one by adding multiple dithering modes. You can choose them by pressing the keys 1 to 4. First mode is nearest color, no dithering. That's what we are seeing here. The second one is called Buyer 4x4 ordered dithering. Yeah, not very good for this picture, but sometimes good on other pictures. The third is called 1D scanline error diffusion, and it takes a long time to calculate. That is one of the reasons why this dithering mode won't work in a game. And even with all that long wait, it wasn't a nice picture. And then my favorite, the Sierra style 2x2 stippled mode, inspired by Sierra Online's dithering techniques for old CGA games. By dithering, the program can simulate even more colors than those 3 per scanline, making images look smoother and more detailed, especially in areas with subtle color gradients. Like the BMP2 viewer, black is always reserved for the background and border, and all color magic happens in entries 2 to 7 in the CGA through the CGA palette flipping. I also experimented with reprogramming entry 7, the one normally reserved for black, to gain a 4th color on scanlines that doesn't actually use black. This technique works, but in practice the benefit is minimal. Almost every scanline in real images already has some black pixels, so the extra color slot is rarely useful. Worse, reprogramming entry 0 also changes the border color, causing visible color border artifacts. That's why the final versions keep entry 0 permanently black. It's a trade-off I tested, and I decided it wasn't worth it. I also tried changing palette colors mid-scanline, the idea being that if I could update the palette not just between scanlines, but also partway through one, we could fit more than 3 colors plus black on a single line. Unfortunately, the result was visible flickering and artifacts. The graphics chip's palette write protocol simply takes too long to complete cleanly during the visible portion of a scanline, so any mid-line update becomes visible as a glitch. In the end, 3 independent colors plus black per scanline turned out to be a practical limit for a stable-free output. And that brings us to the end of this endeavor to explore my Olivetti Prodest PC1. It's been a strange, fun, and sometimes frustrating journey. Digging into undocumented features, hitting weird hardware quirks, and discovering tricks I never thought were possible on a PC from the 80s. But the truth is, there is still so much left to uncover. There are techniques I haven't tried yet, hardware behaviors I still don't fully understand, and definitely a lot of assembly code that can be cleaned up, optimized, or completely rewritten. This machine keeps surprising me, and I'm sure it still has secrets waiting to be found. I hope this video inspires you to try developing for the PC1 as well. It may be obscure, but that's what makes it exciting. Every discovery feels like uncharted territory. All the programs you've seen here today are created entirely by me, and the full source code, notes, and documentations are available on my GitHub. If you want to study the code, improve it, or build your own experiments on top of it, everything is there. Thank you so much for watching. If you enjoyed this deep dive into forgotten hardware, please press like and feel free to leave a comment. I'd love to hear from you, your thoughts, your ideas, or your own experiments. See you in the next one.